Hello, everyone. I'm Jixuan Liang, a second-year PhD student from Lab at the University of Hong Kong. Today I'm delighted to introduce our new work Skilldiffuser, Interpretable Hierarchical Planning via Skill Abstractions in Diffusion-Based Task Execution. It has been accepted by CVPR2024. This collaborative work was done by HKU, UC Berkeley, and Shanghai AI Laboratory. Please check our project page to find more details. This is an outline of this presentation. Firstly, I'll give a brief review of the background on planning with diffusion model. Recently, diffusion models have become prominent generative tools in a wide range of fields. In the context of planning tasks, previous work, Diffuser, has innovatively applied diffusion models to trajectory generation. This approach treats state trajectories as single-channel images and utilizes a diffusion model to denoise the whole trajectory in a single operation, achieving enhanced performance in multiple tasks like Jim-Mujoko, Maze 2D, and so on. However, their ability to generate coherent trajectories for intricate tasks still poses challenges in terms of performance and generalizability, as these tasks require the completion of abstract instructions comprising multiple sequential subtasks. Some follow-up works, such as Decision Diffuser, try to solve this problem by decomposing complex tasks into simpler subskills, organized within a predefined skill library. These methods rely on conditioning the diffusion model with one-hot skill representations for each of these subskills, but encounter difficulties in attempting to autonomously learn end-to-end from a wide range of datasets, which hinders their scalability. Inspired by the observations, we propose Skilldiffuser, a hierarchical planning framework, capable to interpret and execute complex instructions with higher transferability. Now, I will delve deeper into our approach. As the figure illustrates, Skilldiffuser is a hierarchical planning model that leverages the cooperation of skill learning at the higher level and a conditional diffusion model at the lower level for task execution. The high-level skill abstraction firstly generates learnable subgoals, and then the low-level diffusion model is employed to condition on the subgoals to determine the appropriate future states. Finally, future states are converted to actions using a separate inverse dynamics model. The high-level skill abstraction module consists of a skill abstraction component upon a horizon-based skill predictor adapted from GPT-2, and a vector quantization operation which enforces each learned skill to lie in the skill set. As each instruction may be broken down into different length subskills, we apply a horizon-based skill code embedding. The low-level skill condition diffusion planning is based on the classifier-free diffusion guidance, which amplifies the features of high reward or optimal characteristic through the diffusion model directly, with the condition as part of its input. A detailed proof is provided in the appendix. The architecture of low-level skill condition diffusion planning module is shown here. We apply a U-Net-based diffusion model with learned skill embedded in the convolution block. A separate inverse dynamics model is trained simultaneously. Under this setting, we engineered a threefold loss function. And a pseudocode of our algorithm is shown here. Subsequently, let's see our experimental results. We tested our method on Laurel Sawyer dataset and MetaWorld MT10 tasks. Please check our paper for more details. First, about the overall performance, we show the evaluation results on Laurel Sawyer dataset here. We compare our method with random policy, LCBC, LCRL, LangDT, and state-of-the-art LISA, and prove our model's robustness in handling varied skill representations, marking a notable advancement in skill condition diffusion model. We also test the rephrasal-wise performance of our model, which shows nearly 10 percentage points higher than the previous SOTA, demonstrating its strong robustness against ambiguous language instructions. For the long horizon instruction performance, we conduct experiments following the same settings of unseen composition tasks of LISA with 12 composition instructions in Table 3. We observe Skilldiffuser achieves 2x performance of non-hierarchical baseline and also improves about 25% over LISA, highlighting its effectiveness. Then, an ablation study is conducted on MetaWorld. We evaluate our method against 3 baselines, all modified from existing models. From Table 4, it's obvious that each component of our method, especially the skill abstraction and the diffusion planning module, is important. Besides, we complete the ablation on reusability and interpretability of learned skills. For reusability, we observe each single instruction uses 1.55 different subskills on average for a single instruction, and each skill is called multiple times than the number of instructions. We also visualize resulting images from applying discrete skills to further validate skills interpretability. The figure 4 shows the visualization of learned skill set. This indicates not only a significant interpretative advancement over previous diffusion-based planning, but a successful abstraction of high-level skill representations. In addition, we also visualize the learned skill word clouds, which demonstrate strong robustness to ambiguous language instructions. For instance, Skill 4 effectively abstracts the skill of open a drawer from ambiguous expressions such as open a container, pull a dresser, and so on. Lastly, we explore the effectiveness of condition guidance weight in Table 9. We find the guidance weight slightly greater than 1 helps the planner's performance. Finally, here comes the conclusion of our paper. We propose Skilldiffuser, an integrated framework that enables robots to perform tasks from natural language instructions by enabling interpretable skill learning and conditional diffusion planning. Extensive experiments highlight our method's effectiveness. If you are interested in our work, feel free to contact with us. Here are the QR codes about our project page and my personal page. That's all. Thank you.